let's try to take some time today and let's derive some equations and so forth, okay? So the first thing I want to do is I want to go through the absolute basics for harmonic motion. If you look down here, I have an object that is two springs hooked up so that you can see harmonic motion. On worksheets and so forth, a lot of times they'll show an idealized spring that somehow doesn't tip over. How that happens, I don't know. That's why I have two. You'll notice when it's at rest, that's the equilibrium position where x equals 0. If I make its displacement positive, which way is the spring pushing?
What?
That way. And then if I have a negative displacement, the force is pointing forward. As we found in the last class, we found that as we doubled the displacement, or we doubled the force on a spring, its displacement doubled. We tripled the force, the displacement tripled, and that gives us this first equation, or the first rule for harmonic motion, that the force is proportional to and opposite the displacement. The equation that we have that we use is F equals negative kx, otherwise known as Hooke's law. When you double x, you double F, and vice versa. Okay? Then, if we set that equal to F equals ma, so we have F equals negative kx equals ma, and we solve for a, we get that a equals negative k over m times x.
Yeah.
And what do we have? We have that a is proportional to x as well. There's rule number 2, that a is proportional to negative x, or a equals negative k over m times x. And you know, we worked out that a is actually the second derivative of the position, isn't it? Which we wrote right this way. That would equal dv dt, which equals d squared x over dt squared. That simply says is the second derivative with respect to time. Which gets us our third and our most important. Fortunately, I ended up in black. Now, I want to show this even more so. This is what we get down to simple harmonic motion. That, pretend the x's aren't there. If the second derivative of something is proportional to that something and in the opposite direction, that's simple harmonic motion. In your worksheet, you actually had an instance that I showed you using inductors, and you didn't need to know what an inductor was. But if you just watched what was going on and followed the math, we ended up with this equation. And you can see, there's Q, there's Q. There's the second derivative of Q. There's a constant of proportionality. And there's the negative. So obviously, the second derivative of something is proportional to that something and in the opposite direction. Whatever this is, it's simple harmonic motion. That's why this definition is the most important. Because if these both are dependent on x and t, or sorry, dependent on position. This one's not dependent on position. Now, next thing I'd like to talk about. Let's imagine we have an object in a circle. If I were to have a circle, and I were to put like a peg on the circle, and the circle is doing this, and we were to project a light down this direction. When the circle is going like this, wouldn't you get? I'm doing that pretty well, actually. And then here. I was a conductor for years. I can do two things with one with each hand. Yes, did we see it? Okay, that might even have been easier than what they were doing. Okay, did you see it though? And if I were to project this into one dimension, you can see it starts to look like this, doesn't it? Yes? Now let's break it down and actually take a look at it. So we'll draw a circle here. And we're going to take these positions. Position 1, position 2, position 3, position 4. And here we go. Here's our velocities. An object at constant velocity going around a circle. Those arrows should be the same length. They're probably not. would you agree if this is the circle, then this is my distance from the circle is r? And right back in on itself in all cases is an acceleration. Because it's centripetal, it's going to point to the center of the circle, isn't it? A lot on that circle. Can we see it? Now let's break this down. In the x direction. In the x direction, where this is my position, my x velocity, and my x acceleration. Well, if we look, it starts off right here. You see how if this is 0, then it starts in the x direction way over here, doesn't it? At a maximum. Then it goes to 0, and then a minimum. In the x direction, it goes maximum, 0, minimum. Maximum, 0, minimum. And then want to go back at number 4, want to be at 0 again? Which gives me what kind of graph?
Cosine.
That's a positive cosine graph. Now let's look at the velocity. Does that have any horizontal velocity right now?
No.
No, 0. Now it's
Maximum.
negative. It goes 0, negative, 0, positive. 0, negative, 0. 0, negative, 0, positive.
Negative
which is
sign.
a negative sine graph.
That's it before badly.
Now let's look at the acceleration. Right here, you see how my acceleration is? Negative, and my horizontal, in the x direction, my acceleration is 0, and now positive. So negative, 0, positive. Which is a negative cosine graph. You look there, what's the derivative of that point? 0, negative, 0. What's my slope there?
Negative.
0, positive.
Positive.
Because this is the derivative of that, etc. Now what we just proved was that the derivative of the cosine function gives me the negative sine function, and the derivative of the sine function gives me the negative cosine function. And not just because the calculus books say so, but because it is true physically.
Yeah.
Then, if we look in the y direction, well, that ain't sure ain't gonna work.
Nice.
Yeah,
Nice done.
Yeah, that tells you how bad it is when my students are all impressed when I make a layup.
It's like the second time this year.
Yeah. So here we go in the y direction. So let's look in the y direction, starting at point 1.
Negative.
No, x. So position. Is it still right here?
Oh.
So it's 0, because this is the y component, right?
Yeah.
So if this is 0 in the y direction, then it goes negative, 0, positive. So 0, negative, 0. Which is a negative sine graph. Now the velocity. In the y direction, the velocity is negative, 0. That's horizontal. That's not vertical, is it? So negative, 0. Which is a
Negative cosine.
negative cosine graph. And the acceleration right there. Any vertical acceleration?
Nope.
So it goes 0,
Positive.
positive. Which is a
Sine.
positive sine graph.
On your worksheet, didn't it say that like circular motion in the y direction wasn't simple harmonic motion?
Well, yeah, that's actually something, let's talk about this real quickly. So let's look at this point right here. We said that one of our tenets of simple harmonic motion is that the acceleration is proportional to x and in the opposite direction. Look right here. The acceleration is this way. The velocity is that way. Those are not in opposition at all, are they? At no place on this circle is, well, if this is the velocity, isn't the displacement going this direction? Right now, it's moving this way, but the acceleration is that way. Circular motion is not harmonic motion. It does not go through the center and restore itself. Because this, when we do this, doesn't it go over the same path? A pendulum, doesn't it go over the same path over and over? That never goes over the same path. But when you break it up into its x and y components, it looks like harmonic motion.
Indeed.
Matter of fact, let's prove one other thing, just why not? Before we'll get onto other things here, but. So if we were, let's figure out our equations here. So our x equation, so what's our maximum x gonna be? R. So x will equal our maximum, our amplitude, which is R. And it's gonna be a cosine function. And we could put a theta there, because the theta is changing, but we should know that theta equals omega t. Where this is in radians per second, times seconds gives me radians. Why would I want to convert from theta to omega t?
Because t is your actual variable.
Because I'd like to know where it is over time. And in physics, we don't just want to know at some position. If the thing is moving, we would like to say at this moment in time, what's its position, what's its velocity. All of physics is defining the universe. And so you always want to know its kinetic energy, its potential energy, its position, its acceleration, etc. Okay? So we get this. Now my velocity. My velocity is going to be, its maximum velocity is going to be v, but it's going to be a negative sign graph. We'll substitute there in a bit. And my acceleration will be a maximum acceleration of a, but negative cosine. I can do the same thing over there in the y direction as well. I'm only going to do one of them right now. This one is going to be y equals negative r sine omega t. These other ones I'm not going to need for right now. But I want to prove something before I go any farther. So if I convert that back to sine theta, would we agree at any given point, if I pick a point on that graph where that's theta,
Yep.
this is r, this is y, this is x. By Pythagorean theorem, we know that x squared plus y squared equals r squared, yes? Well, let's take our equations here. If we say that r squared equals x squared plus y squared, r squared equals r squared cosine. Can I just call it theta for right now to make this easier? Because we know that omega t is just theta, right?
Yeah.
Plus, and if you square that, doesn't a negative times a negative give me a positive?
R squared.
Which gives me r squared sine squared theta. I pull the r squareds out, and I get that cosine squared plus sine squared. And if these two are here, then obviously cosine squared plus sine squared equals
I'm
1.
guessing that is definitely how they.
Dang.
Do we, now again, the reason I want to do this is I want to prove things to you, not just tell things to you.
Yeah.
And didn't we just prove that cosine squared plus sine squared equals 1?
I don't believe it.
You can do that so nonchalantly.
Yeah.
You guys didn't even know that was coming, did you?
What?
No, I saw it.
You didn't see it coming?
I saw it coming. I saw it coming when you started plugging stuff in. I was like, yeah, that's okay.
Now, would you agree that in all the other cases, down in all these other cases, if I took my Vx and my Vy, then V squared x, Vy squared x would equal V squared, and the sines and the cosines would be, you'd have a sine and one and a cosine, they'd both be squared, and they would disappear again. Because in each case, if I pick any place on this circle, then you're gonna get the x squared, or the x acceleration, the y acceleration, will add up vectorially to give you a. And the a is a constant, r is a constant, v is a constant as it goes around the circle. What is my greatest displacement? R. What is my greatest velocity? V. What is my acceleration? A. In other words, as this is going around, we could pick numbers, couldn't we? We could say an object is going around the circle at 3 meters per second, it has a maximum displacement of 2 meters, and we could work out all these numbers. But we're trying to do this with variables to prove that they all work for everything. We good so far? Okay, now I want to do one more thing that we did last time, but I want to prove it one more time. If we take this object on the circle again, we said that if this is a circle here, and this is r, this is theta, this is x, we can see that x equals r cosine of theta. Which we also figured out by just following an object around it. Well, then we could also say that at this point right here, we have its velocity. You hopefully can see that as this closes at the top as well. Do you see that?
Yes.
That if you take my thumb right here as the vertical, I made this vertical, you can see that this is opening here at the same time that this is opening. Therefore, those thetas are the same. Let's make it bigger so that we can see it. And we get, this is our vertical, here's our velocity, theta. This would also be theta. We good so far?
Yeah.
And this would be my Vx. And it turns out that Vx is the negative V sine theta. And then if we look at our acceleration, which is always inward, our acceleration is always this way. There's theta. There's the x component of acceleration, which is obviously negative. And it's cosine. So in other words, we can get these equations, whether or not we follow an object around a circle and graph it, or if we stop it at one point in time, and we figure out what the equations would be. And by the way, all of those ones we got for the y direction, we could do the same thing. Now I'm going to substitute a couple more things in here so that we get one more moment, which we did, I think, the other day as well. We got that theta equals all this. Well, we also know that omega equals v over r. Remember that? We've done that several times. Well, then we can solve for v, which equals r omega. We also know that that centripetal acceleration, ran out of space, I apologize. Centripetal acceleration is v squared over r, isn't it? Well, v is this. I'm going to plug it in. I get r squared omega squared over r, which tells me that a equals r omega squared. Yes or no?
Yes.
Okay, I'm going to square these just so that we can find them easily. And we already put that one in, but those are important. Well, now we get this. I'm going to put in that v equals r omega, negative r omega, sine omega t, and a is r squared omega. And I give you the chain rule from calculus. Those of you that are not in calculus obviously don't know what I'm talking about. Those of you that are in calculus can see it, can't you? That you take the derivative of the whole thing times the derivative of the inside. What's the derivative of omega t with respect to time? Well, it's just the constant, omega. Just like if you took d dt of at, if a is a constant, gives you just a. Do we agree with that? Yes? Well, in this case, a is omega. So it's the derivative of cosine, which, see how we worked it out? Cosine goes to negative sine. So to do this the long way would be this. X equals r cosine omega t. The first derivative with respect to time will equal r times the derivative of cosine omega t. Sorry, that's negative sign. That's dumb. Sorry. Oops. Oh yeah, so let me do this the long way. It would be d dt of the cosine of omega t times d dt of omega t. That's the chain rule. And that gives me the derivative of cosine. Yeah.
Shouldn't it technically be d, for the cosine, should it be d omega t, because now you've included the,
Well, I don't know, again, I don't know how Cleveland writes this, how they do this in calculus. But I know it's the derivative of the cosine.
yeah.
At times, and I don't know how you guys actually write that.
Well, because technically by writing that, you're saying you haven't
Well,
done
then how
anything.
do I
Well,
write
the
this?
omega
Basically
is
that?
a
You would
constant.
just have t, and you would just be
Is it that?
pressing t.
Yeah.
Is it that?
Or, I mean, you would say, for the ddt, you would say dd omega t, because you already have taken the omega out.
I thought,
No, I haven't taken the omega out yet.
Well, I mean, you've separated it.
Well, whatever it is.
Yeah.
I don't know how you guys write that, but it's gonna be.
There's no formal way to, we don't.
Let's come back. So, we're gonna have the r still, the derivative of the cosine, which is going to be negative sine omega t, times the derivative of the inside, which is omega. And that gives me negative r omega sine omega t.
Yeah.
And that gives me the velocity. Then I take the derivative again, which is dv dt, which equals, by the way, I'm gonna draw, the second derivative with respect to time, which is my acceleration, yes? Take the derivative, the constant stay. The derivative of sine is cosine, times the derivative of the inside, which gives me the second derivative with respect to time of x, which is my acceleration, equals negative r omega squared cosine omega t. Do we all agree with that? Now let's look. You see r and cosine omega t? Isn't that x? Which means that a equals negative omega squared x, or that the second derivative with respect to time equals some constant times x, which is our definition of simple harmonic motion. And if we were to take this to be a spring, where for a spring we get the acceleration equals negative k over m times x, do we have to go back and derive that, or do we remember that? Well, let's just do it and I'll put it over there, okay? So we get that for a spring. F equals ma, negative kx equals ma, that a equals negative k over m times x. Oh yeah, we have it right there, don't we? We've got it right there.
Yeah.
Okay, I thought we had done that. So, we look here, we say, hey, that's acceleration, so's that. That's x, that's x. Therefore, we can set them equal, and we find out that omega squared equals k over m. Which says that omega is the square root of k over m. I don't think I took the time to talk about omega yet, have I? Even though you did it on the worksheet, but let's talk about omega. When something's moving, we have basic definitions. Our first basic definition is amplitude, which is the farthest position. So if I take this and I push it all the way, so if this is 0, I'm just going to do it easier from here. If this is at a beginning position, and I move it to here, well, I've got half the length of the car. That would be its amplitude, would be half the length of the car, which would be the greatest position. That does not mean that's where it's always at, is it?
No.
I mean, couldn't it be right here as well? But so its x position does not have to be A. Does everybody understand what I just said?
Yeah.
If this is the maximum position, that's saying that's where its maximum is, but it could be anywhere in between those two maximums. It can't be greater than the maximum. Yes? And then, it's got some sort of period that's happening over and over and over. Well, we could call that t, its period, in seconds. We know that its frequency is 1 over t in hertz, or 1 over seconds. And then we have this omega. And omega we define as, I guess I'll put that over here. Omega is defined as 2 pi over big T in radians per second. How many radians it travels in 1 second? Well, if it does an entire circle, how many radians is that?
2 pi.
2 pi. And since, remember, a circle going like this looks like harmonic motion, Yes? Well, then one complete circle is one full cycle, which is 2 pi radians. So if it does one circle per second, that equals 2 pi radians per second. That means one cycle per second. So start 1001, 1002, 1003, right? So it does an entire cycle every second. If it were pi radians, then it would do pi radians per second, which is half a circle per second. 1001, 1002, 1003, 1004, 1005, 1006, so I'm not sure if I can do this. See. It would take me a while. I could do that. It would just take me a couple of seconds to figure out how to do both of them. So, looking over at what we just found, and we're going to write this one down as well. Equals square root of k over m. And I will tell you, this is the one that I have the hardest time remembering in this chapter. I have the hardest time remembering this. I'll get to those when I can. Thank you. Now let's take these two values that we just wrote. You can work on that later. Let's take these two values that we just found, and let's set this equal to 2 pi over t. And then we solve for t. T goes up this way. The 2 pi stays. This reverses square root of m over k, which is the equation for the period of a pendulum, which is up there somewhere. Right there.